So one of the questions that's come up in the discussion forum, particularly about vector-borne diseases, are strategies for the genetic engineering of vectors. In fact, this idea that we can change actually actively select for changes in the vector population, either through the introduction of new genetic variants or through changes in selective pressures, to try and select vectors that are either just simply less effective at transmitting diseases or perhaps completely incapable. And so these are strategies that have been applied in various different types of insect pest management in the past. There are some trials going on currently in South America right now looking towards prevention of both dengue and the prevention of the spread of chikungunya. Both are diseases that have come up quite a bit in the discussion forums, because we have a lot of learners who are actually experiencing those outbreaks currently.
Chikungunya just got into southern US also, isn't that right? Haven't there been? Is there?
Yes, there. So again, there are. So we have the vector now. Well, there are two key vectors. Anopheles, Aedes aegypti, Aedes albopictus. Aedes albopictus is a new invading mosquito, and so chikungunya is probing the US constantly. There have been a couple of cases, I think, of sort of autochthonous transmission in Florida now.
Mm-hmm. So well, one of the questions is just to bring this to the group who perhaps aren't familiar with this. How do we go about introducing genetic change or making use of artificial selection in this massive vector population? How does this actually work? That these new genetically engineered vectors can have an impact.
So there are two parts to the technologies. One is to introduce something which affects a change, that is making your mosquito less competent to transmit malaria. And that could be by manipulating its immune responses. Most mosquito vectors, when they're challenged by the pathogen they transmit, that still evokes some sort of immune response. So we might be able to boost that, make mosquitoes less competent, less able to transmit malaria. Or we could play with other life history traits of the mosquito themselves. We could kill them, we could life shorten, we could stop them flying, we could impact on their ability to search for blood meals or whatever. Or reproduce. So there are ways of reducing the capacity of the mosquito to transmit. And then the second component of that is, how do you get it to spread? Right. I mean, you can create that in the lab, it's perfect. You can create a perfectly refractory strain, and then you want to throw that out the door and get that to spread across Africa or spread through Central America. So you need some sort of drive mechanism. And there are, you can sort of do, in a way you can sort of achieve that in two ways. One, you can actually have a genetic drive mechanism, something which causes a gene to spread and in non-Mendelian ways, something that gives it an advantage. And there are a range of sort of techniques that can do that. And the other is actually you sort of do it by brute force, you do it by numbers. And if you've got a low background, relatively low density vector population, and you can mass produce millions and millions of vectors that carry this trait that you're interested in, particularly if it was one that sort of confers sterility or something, you can actually mass release millions and millions of these things, get them to swamp out your resident vector population and cause local elimination. So both of those things have strategies. I think the people have looked at this for a number of years, been researching this for a number of years, and then there are a range of candidate techniques for which we can reduce capacity of the vectors to transmit. Mm-hmm. Marrying those with an appropriate drive system is actually where the challenge is. The sort of two that have got most traction for Aedes and Aedes mosquitoes, certainly Aedes aegypti for transmitting dengue and chikungunya, one is through Wolbachia, which is a bacterial endoparasite, which has the advantage of it basically has a non-Mendelian drive mechanism built in, so it's able to spread through populations. There's sort of an interesting twist that most insects carry Wolbachia, but the ones we really, really care about, the key vectors like Aedes aegypti and the Anopheles, don't have Wolbachia. So a big part of the research program has been to try and introgress Wolbachia into these populations and then allow the Wolbachia to spread.
So we haven't actually, I don't think we haven't talked much about Wolbachia in the course so far, and I don't work on it, but it's incredibly interesting biology. So I don't know if you or Andrew maybe can just talk a little bit more about the wonders of Wolbachia.
So it spreads. So it spreads through.
What is it to begin with?
So it's a bacterial endosymbiont. And it's generally maternally transmitted. So if you get it into your germline, then basically you maintain it. There's some rare horizontal jumps between species, and it spreads through. It can have a range of sort of consequences for the organism carrying it, which could include life shortening, could include sterility, could include changing sex even, and it spreads through.
And then in some cases, it actually prevents mosquitoes from being susceptible to some.
So that was the interesting thing about the discovery of the original approach in trying to introduce Wolbachia into these mosquitoes which didn't have it. The idea was that it would carry a cost and it would shorten the life of the mosquito. And if a mosquito doesn't live very long, it reduces its chance of transmitting the disease. All of these diseases, like dengue and malaria, have a long incubation period in the mosquito. So they don't simply act like passive syringes. So if they were to pick malaria up from you, it would then take them about 2 weeks for that mosquito to incubate the parasite before it could fly on and transmit to somebody else. So if you could stop mosquitoes living for 2 weeks, there'd be no malaria and there'd be no dengue. That's all you need to do. That's all you need to do. And in fact, most mosquitoes don't live for 2 weeks. It's only a small tail, only a small proportion of the population which live for that 2 weeks, 3 weeks, 3 weeks plus that are responsible for the transmission. So if you could introduce something which had a fitness cost that slightly shortened life, then you would stop mosquitoes transmitting malaria. And that was the original idea. And they found a Wolbachia strain which they were managed to introgress into the mosquito population, which had this life-shortening effect. The problem is that the more life-shortening you are, the harder it is for the parasite to spread. The more cost it has, the more difficult it is to get it to introgress into the population. So there was this tension between life-shortening and fitness cost and actually getting to something to spread. And it was relatively fortuitous that they hit across another strain of Wolbachia which didn't have such strong life-shortening effects, but had very big transmission blocking effects. So if it turned out that if you were infected if you were infected with the Wolbachia, you couldn't then become infected with dengue. So that's now changed the strategy